All right, so you ready to, like, dive into this cosmic mystery?
Always.
It turns out that, like, creating a galaxy may be a lot like cooking Christmas pudding.
Oh, wow.
I know, right?
So today we're going to crack open this paper from the December 20th edition of the monthly notices of the Royal Astronomical Society.
Okay.
And the title is a mouthful, but here it is. Polarized dust emission in ARP 220. Magnetic fields in the core of an ultra-luminous infrared galaxy.
Wow. That's a title?
It is, right. So we're about to find out if scientists have finally found, like, this secret ingredient that makes some galaxies so incredibly efficient at birthing stars.
Yeah, this is a question that has puzzled astronomers for decades. You know?
Yeah.
Why do some galaxies seem to just churn out stars at such an astonishing rate?
Yeah, it's crazy, right?
It is. And this paper suggests that the answer might lie in something that we can't even see.
Oh, really?
Magnetic fields.
Okay, so before we get too far, can you remind me why we're even talking about magnetic fields in space?
Sure.
Because they're invisible, right?
They are invisible, but they exert a powerful force.
And this research is providing, like, the first real observational evidence that they might be the key to understanding how galaxies create stars so efficiently.
Okay.
You know, think of it like this.
Yeah.
You've got all this gas and dust.
Right.
The raw ingredients for stars just kind of floating around in a galaxy.
Yeah.
But without something to hold it together,
Yeah.
it would just dissipate.
So you're saying these magnetic fields are acting like this giant cosmic net
Yeah.
that's keeping all of those star-forming ingredients from just flying apart.
That's a great way to think about it.
Okay.
The researchers used the Submillimeter Array, or SMA,
Okay.
in Hawaii to study a galaxy called ARP 220,
Okay.
which is actually two spiral galaxies in the process of merging.
ARP 220, that's one of those ultra-luminous infrared galaxies, right?
It is, and that's a critical detail.
Okay.
Because ultra-luminous infrared galaxies emit huge amounts of energy, mostly in the infrared part of the spectrum. This intense infrared glow is a telltale sign that a galaxy is experiencing a burst of star formation. Meaning stars are being born at a rate that dwarfs a typical galaxy like our own Milky Way.
Oh, wow.
What's fascinating about this research is that for the first time ever, they were able to detect magnetic fields within a dense disk of gas and dust right at the core of ARP 220.
So we know that these ultra-luminous galaxies are like star factories on overdrive, right?
Right.
But why is emerging galaxies so important to this discovery?
Well, when galaxies collide, it's a cosmic event of epic proportions.
Yeah.
Imagine all that gas and dust getting churned up,
Yeah.
heated, and potentially blasted away.
Right.
But the magnetic fields, they might be the force that keeps everything contained like a lid on a pressure cooker.
Wait a minute, the paper mentioned a pressure cooker analogy.
It did.
So instead of steam and vegetables, we're talking about gas and dust getting cooked into stars.
Precisely.
Wow.
The analogy helps to visualize how these magnetic fields might be concentrating the gas and dust, creating the ideal environment for stars to ignite and form.
Okay.
And this isn't just a theoretical concept anymore. This observation in ARP 220 is the first concrete evidence we have to support it.
This is starting to make sense.
Yeah.
So these magnetic fields are like the missing piece of the puzzle, explaining why merging galaxies are so good at forming stars.
Right.
But how did they actually detect these magnetic fields? I mean, we can't see them with our eyes.
Right. That's where the submillimeter array comes in.
Okay.
It's a collection of radio telescopes that are specifically designed to observe light at millimeter wavelengths.
Okay.
It turns out the dust grains, which play a critical role in star formation, emit polarized light at these wavelengths.
Polarized light.
Yeah.
Can you remind me how that works?
Sure. Imagine light as a wave
Okay.
that can vibrate in any direction.
Okay.
Polarized light is like a wave that's forced to vibrate in only one direction. The really cool thing is that the direction of this vibration can be affected by magnetic fields. Oh, wow.
By analyzing the polarization of the light coming from the dust in ARP 220, the researchers were able to infer the presence and orientation of the magnetic field.
So it's like a cosmic fingerprint
Exactly.
revealing the invisible forces at play.
Exactly.
That's pretty amazing. It's like they've found a way to see the unseen, to
Yeah.
understand this fundamental force that's shaping the universe.
Right.
But if magnetic fields are this important, why don't we see them in every galaxy?
That's a great question, and it gets to the heart of why this discovery is so significant.
Okay.
We don't know for sure if these strong magnetic fields are unique to merging galaxies like ARP 220, or if they're present in all galaxies just waiting to be detected. It's also possible that the strength and configuration of these magnetic fields vary from galaxy to galaxy, which could help explain why some are more prolific star formers than others.
So this is just the tip of the iceberg, so to speak.
Okay.
What are the next steps for the research team? Are they planning to look for these magnetic fields in other galaxies? Absolutely. They're already gearing up to use an even more powerful telescope called ALMA, which stands for the Atacama Large Millimeter Submillimeter Array.
Wow.
It's located in Chile, and it's capable of observing light at even finer detail than the SMA.
So what's the advantage of using ALMA?
ALMA's increased sensitivity and resolution will allow them to search for similar magnetic fields in other ultraluminous infrared galaxies, but also in different types of galaxies that might be less active in star formation.
Okay.
This will help them determine if this phenomenon is widespread or if ARP-220 is a special case.
Okay, so this is clearly a major discovery.
It is.
But I'm curious, beyond just looking for more magnetic fields, what other research directions does this open up?
This discovery is going to have a ripple effect throughout astrophysics. For example, understanding how magnetic fields influence star formation could also shed light on the formation of other celestial objects like planets and even black holes. It could even help us refine our models of galaxy evolution, giving us a clearer picture of how galaxies form, grow, and change over time.
I'm starting to see why this is such a big deal.
Yeah.
It's not just about understanding one galaxy. It's about understanding the fundamental processes that shape the universe.
Exactly.
I'm curious, is there any way to connect this discovery to our own galaxy, the Milky Way?
That's where it gets even more interesting.
Okay, I'm ready for the next layer of this cosmic onion. Let's unpack that in part 2.
Well, while we haven't directly observed these kinds of magnetic fields in the Milky Way yet,
Right.
it's fascinating to consider that similar processes might have been at work during its formation.
So you're saying our own galaxy might have had a magnetic boost early on,
Yeah.
helping it to churn out like the billions of stars that we see today.
It's certainly a possibility.
Wow.
You see, the Milky Way is thought to have undergone a number of mergers with smaller galaxies over its lifetime.
Right.
If these mergers triggered starbursts fueled by magnetic fields, it could help explain how the Milky Way grew into the massive spiral galaxy it is today.
That makes me think about something that you said earlier.
Okay.
You mentioned that understanding how magnetic fields influence star formation could also impact our understanding of other celestial objects,
Yeah.
like planets.
Uh-huh.
Can you elaborate on that a little bit?
Absolutely. We know that planets form from the disks of gas and dust that surround young stars.
Right.
If magnetic fields are playing a role in shaping and controlling those disks,
Yeah.
they could also be influencing the types of planets that form, their size, their composition, even their orbits.
That's incredible.
Yeah.
So this one discovery could potentially have implications for everything from like the formation of galaxies to the formation of planets.
It really does.
It really highlights how interconnected everything is in the universe.
Exactly.
Wow.
And this is just scratching the surface. There's so much more to learn about how magnetic fields operate on a cosmic scale.
Speaking of learning, I have a confession to make. The paper kept mentioning far infrared.
Yeah.
And I have to admit, I'm a little fuzzy on what that actually means and why it's so important here.
That's a great question, and it's crucial for understanding how astronomers are even able to study these phenomena.
Okay.
You see, light comes in a wide range of wavelengths.
Right.
And far infrared is a specific portion of that spectrum.
Okay.
What's unique about far infrared light is that it's emitted by cold dust. The same kind of dust that's the building block for stars and planets.
Okay, so it's like the dust is glowing in this far infrared light.
Yeah.
But why is that so significant for studying star formation?
Because by observing the far infrared emissions from a galaxy, astronomers can tell how much dust is present and where it's concentrated. And since dust is a key ingredient for star formation,
Right.
these emissions act like a beacon highlighting the regions where stars are actively being born.
So when we see a galaxy glowing brightly in far infrared, it's a pretty good bet that it's like a hotbed of star formation.
Precisely, it's like looking through a special filter that lets us see the universe's stellar nurseries.
That makes me think back to ARP-220.
Okay.
The paper described it as effectively boiling over from all the young stars and supernovae.
Yeah.
That sounds pretty intense.
It's a chaotic and dynamic environment.
Wow.
Imagine two massive galaxies colliding with their stars' gas and dust all swirling together.
Yeah.
It's like a cosmic blender on high speed.
Yeah.
And in the midst of all that chaos, these magnetic fields are somehow managing to maintain a sense of order, channeling the gas and dust into the dense cores where new stars are born.
It's amazing to think that something invisible to our eyes could be playing such a pivotal role in shaping the universe.
It's a humbling reminder that there's so much we still don't know about the cosmos.
Yeah.
But with each new discovery, we're getting closer to understanding the fundamental forces that govern the universe we live in.
This has certainly been an eye-opening deep dive.
Good.
Starting to see the universe in a whole new light, or should I say a whole new wavelength. Speaking of uncovering secrets, I'm curious about one more thing.
Okay.
Earlier you mentioned that this discovery could even have implications for our understanding of black holes.
Right.
Now, that's a topic I can't resist.
Yeah.
Let's explore that in part 3. Okay, so black holes, I mean, you can't just mention black holes and not elaborate.
Right.
How do magnetic fields tie into those cosmic enigmas?
Well, it's all about gravity
Okay.
and the influence magnetic fields can have on the flow of matter.
Okay.
Black holes, especially supermassive ones found at the center of galaxies, are like giant cosmic vacuum cleaners, drawing in vast amounts of gas and dust.
Right. And we've always thought of that process as being driven purely by gravity.
Yeah.
But now we're adding magnetic fields to the mix.
Exactly. It seems those magnetic fields might actually help to channel and direct the flow of matter towards the black hole. Imagine it like a cosmic traffic cop guiding the flow of gas and dust, making the process of feeding a black hole more efficient.
So instead of just a chaotic free-for-all, the magnetic fields are creating a more organized buffet for the black hole.
That's a great way to think about it.
That's wild.
And this could have huge implications for our understanding of how black holes grow and evolve.
Right.
It might even help explain why some black holes seem to grow much faster than others.
I'm starting to see a pattern here. Everywhere we look in the universe, from star formation to the behavior of black holes, these invisible magnetic fields are playing a more significant role than we ever imagined.
It's a paradigm shift in our understanding of the universe.
Wow.
For a long time, we've focused on gravity as the dominant force shaping the cosmos.
Right.
But now we're realizing that magnetic fields, while weaker than gravity, can still exert a powerful influence, especially over vast distances and cosmic timescales.
It's like we've been missing a crucial piece of the puzzle all along.
Yeah.
And now, thanks to discoveries like the one in ARP 220, we're starting to see the full picture. But I'm curious, what are like the practical challenges in studying these magnetic fields?
Observing magnetic fields in distant galaxies is incredibly difficult.
Yeah.
It requires specialized telescopes like the SMA and ALMA, and even then the signals are very faint.
Right.
It's also computationally challenging to analyze the data and extract the information about the magnetic fields.
So it's a real testament to the ingenuity and persistence of these scientists that they were able to make this groundbreaking discovery.
Absolutely. And this is just the beginning. With new and more powerful telescopes coming online in the future, we're going to be able to probe these magnetic fields in even greater detail.
Wow.
Unlocking even more secrets of the universe.
Well, I, for one, am excited to see what the future holds for this field of research. It's clear that we're only just scratching the surface of what magnetic fields can tell us about the universe. But before we wrap up, I want to go back to something you said earlier about this discovery being a paradigm shift in our understanding.
Sure.
Can you expand on that a little bit?
Of course, for centuries, our understanding of the universe has been dominated by the concept of gravity.
Right.
But now, with the realization that magnetic fields play such a crucial role in so many cosmic processes, we have to rethink our models and theories. It's a fundamental change in our perspective, a shift in our understanding of how the universe works on the grandest of scales.
So it's not just about adding magnetic fields to the equation.
Right.
It's about fundamentally changing the equation itself.
Precisely. It's about recognizing that the interplay between gravity and magnetic fields is far more complex and nuanced than we previously thought. And this new understanding has the potential to revolutionize our understanding of everything from the formation of stars and galaxies to the evolution of the universe as a whole.
Well, that's a pretty profound thought to leave us with. It's amazing how one discovery can open up so many new avenues of exploration and challenge our most fundamental assumptions about the universe.
And that's the beauty of science. It's a never-ending journey of discovery, constantly pushing the boundaries of our knowledge and understanding.
Yeah.
And who knows what incredible insights await us just around the corner.
Well, you've given us a lot to ponder today. Thanks for taking us on this incredible deep dive into the fascinating world of magnetic fields and their profound impact on the universe. Until next time, keep looking up and keep wondering.